Okay, so here's the excuse me, physics review. So let's start at the very beginning. So we started with the idea of force on a charge, force between charges. And that was called Coulomb's law. And what it said was the force between two charges, 1 and 2, and we'll say this is the magnitude, is equal to Coulomb's constant times the two charges, and you will use the absolute value of the charges. So these mean the absolute value, and they divide by the distance between the two charges. So look at test number 1. Okay, so we had these charges that were in line, so you didn't have to worry about the vectors except the directions. So there's going to be something like that on the test. Also from test 1 you had voltages, and that was in 2 dimensions. But the thing about voltage is a scalar quantity, and it's equal to Coulomb's constant times the charge divided by the distance. So you're finding in case of voltage, you're just finding a voltage in space. So you can get a voltage from one charge. If you have 2 charges, you add the 2 voltages associated with those 2 charges. So look at test number 1. Okay. Let's see what else we talked about. We talked about capacitors. So capacitors, there's the relationship between the capacitance, the charge, and the voltage. And remember, charge is in coulombs, and actually here we have the potential, electrical potential, which is volts. And this is coulombs. And the capacitance is in farads. A lot of times the farads are in millifarads or microfarads, so make sure you use the appropriate multiplication. Times 10 to the minus 3 times 10 to the minus 6. You can also do pico and smaller ones as well. And we had that the capacitance for capacitor is equal to epsilon 0, which is one of the 2 main constants, times the area divided by the distance between the 2 plates. So epsilon 0, what is epsilon 0? I think it's 8.85 times 10 to the minus 12, but we will look it up. You can write it on your sheet of paper. It's called the permittivity of free space. So epsilon 0 is 8.85 times 10 to the minus 12th. And the units are Coulomb squared per Newton meter squared. And over here, K is equal to 8.99 times 10 to the 9th or something like that. Coulomb's constant, yeah. 8.99 times 10 to the 9th. and those you have units of newtons meters squared per coulomb squared. You can see the units have just flipped, and that's because there is this relationship between epsilon 0 and k. And but we don't need to worry about that. So also series and parallel simplification of R or C. Okay, so those are the just reducing a group of resistors in parallel and series into a single resistance, and same thing for capacitance. And remember, they're exactly the opposite as far as where you add them together. You deal with the reciprocals. So I'll just write these down for you. So if you're in series, resistor, the equivalent resistance is just the sum of the resistances in a row. If in parallel, you use this reciprocal relationship. Like that. And for capacitors, so these are for resistors. For capacitors, it's the ones that are parallel that you add together. So you get the equivalent resistance is equal to C1 plus C2 plus C3 plus dot dot dot, however many capacitors you have. And in series, we know that it's 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3, so forth and so on. The way I remember it is I remember this one, and everything else comes out. So if this one, you add them together, then that's series. So parallel, it's the 1 over thing. And then I know that capacitors are exactly the opposite. So if you add them together for series resistors, you add them together for parallel capacitors. And likewise, if this is this, then that has to be the opposite. So you only have to remember one of them. If you're trying to memorize them, then just kind of know the pattern. Okay. Also remember, for an the electric field between two parallel plates on a capacitor is equal to the voltage divided by the distance between the plates. So this has units of not newtons, voltages, volts, potential. So it's volts per meter. And back when we're dealing with it in electric field, electric field vector is equal, well, yeah, from a quantity standpoint, this is, if we wanted to calculate the electric field at some point in space, it's equal to K times Q divided by R squared, and the units you get here are newtons per coulomb, but it turns out those are the same. If you simplify them, try to make them equivalent, they will be. They have the same units, even though they might not look like that. Okay, so those were some of the things relating to series and parallel resistors and capacitors. As far as the resistors are concerned, we use Ohm's law to relate current, resistance, and voltage. So Ohm's law says that the current times the resistance is equal to the voltage. Is that right? Does that make sense? And the reason I remember this is because I know that power equals I squared R, and I also know it equals V times I, for voltage times current. And to get this from that, it has to be equal to that if you substitute in for V. So if I solve for R, it's volts per amp, which we call ohms, volts per amps, which we give the name ohm to. We use this symbol, use this horseshoe-looking symbol. So anyway, those relationships are correct. So we got this one relating power to current, resistance, and voltage and current. So sometimes there is a problem in here that deals with relating these things for some kind of resistive element, like a heating element. And so, if you're given power and you're given voltage, you can calculate current. And once you know current, you can calculate the resistance. So there's ways of manipulating these. There's three relationships: power equals this, power equals that, this equals that. And so review that. There'll be something that deals with the power of electric circuits. Now, let me just check something here. Yeah. Also, if you have some kind of resistive element like a wire, so for a wire, Ohm's law applies. So this applies because a resistive element is just a wire of some kind of material. But if you have a wire and that wire is made out of certain material, and that material has what's called the resistivity, and this resistivity has a symbol rho, which is equal to ohms per meter. If you want to actually calculate the resistance, excuse me for just a second. So if you want to calculate the resistance for a wire, you just take the resistivity times the length divided by the cross-sectional area. And you can see if I've got meters per meters, and then you get meters squared, so you end up with meters in the denominator. And so actually the units of that are not ohms per meter. That shows how you can figure out if you make a mistake or not. They actually are ohms meters. So when you multiply resistivity times length, you get ohms meters squared, but you divide by meter squared and it comes out to be ohms. So if you're given a wire of a certain length and of a certain diameter, you could calculate these two things, and if I gave you the properties of the material, you could calculate the resistance. And then given that resistance, you could do further calculations. So you probably see something like that. Okay, so we had all these relationships between force on charges, forces on charges due to magnetic fields, and those turned out to be pretty easy plug and chug relationships. So let's just write them down. Particle, and what we're going to do is show you how you'd remember these things. So you've got a particle moving, and remember we always use a positively charged particle for R, using our right-hand rule when it comes to figuring out the direction of the force. So this is a positively charged particle, and we're looking for the force on that, and of course it probably has something to do with its speed, and it probably has something to do with the magnetic field strength, and it probably has something to do with the charge. And it turns out that's all you need, because there's really no size to this thing. The mass will impact how it accelerates, but as far as actual force, it's not dependent upon the mass. For this case, in case of gravity, yeah, it would be. Anyway, so it's just V B times Q, where this is the velocity, meters per second. This is the magnetic field strength. This is the charge. So that's for a particle, not a, if you spell it correctly. Okay, then you have a wire, and the force on a wire, again, you got these moving charged particles going through here. So you would think it would have to do something with how long the wire is. The longer the wire, the bigger the force. So I think that's a good thing to put in there. Probably has something to do with magnetic field strength. And you know, the velocity charge thing here, actually all is taken into account using the current. And so the length is in meters. This is in Tesla. This is in amps. So we've got all these things kind of taken into account. Current, that's moving charge. Current's charge. So both of these are reflected in the current term. We've got the magnetic field, and then we've got how long this thing is. So that's a wire. Then you have a current carrying loop. And in this case, we don't have a force, but we have a torque. Now, in both of these cases, there's a sign of an angle, but we've been just simplifying it down to these because we've had the magnetic field perpendicular to the velocity and to the current direction. Okay, so here you've got a loop. Think about a loop. So you've obviously got to have magnetic field strength in there again. You've got to have something to do with length. Well, it turns out it's the area, and part of the area gives you the length of the sides that actually give you a net torque. And you also get the moment arm. So these are both taken into account there. And then you have to take into account the charge is moving. So it turns out it's magnetic field strength times area of the loop times the current. So again, Tesla meters squared amps. So those are the three biggies. On the other end of the spectrum, you have calculating magnetic field strength. And this is from due to current. So we really got three cases here. We just got a wire. And if you remember a wire, this is a wire going into the board. And then you're going to have magnetic field lines that go around like concentric circles. And you've got a distance from the center of the wire to some point in space. We'll call that R. And you derive this using Ampere's law. Just turns out it's the current. You would expect that to give you a the higher the current, the bigger the magnetic field. And then you use this mu zero, which is not epsilon zero, then you divide by 2 pi r. So I is current. Mu zero, write that down. It's 1.26 times 10 to the minus sixth. The units are Tesla meters per amp. Okay, So that's the magnetic field around a wire. Then you've got a loop. So the loop, loop is wire that's at a certain radius. There's a radius to the loop. So you've got current flowing around this wire. So the magnetic field strength in the middle of the loop. Again, you would expect if the current is higher, you'd have a higher magnetic field. You expect to use mu0 because that's what you use when you have when you're trying to figure out the magnetic field strength. And I think you don't have R. I think it's just divided by 2R. I mean, you do have R, but you don't have pi. But I'm going to double check that to make sure. Okay. Yeah. And you can also put an N here. So N is the number of loops. R is shown in the diagram. mu0, I amps, R meters. And the last one was a solenoid. And that's a very common thing to use for generating magnetic fields. And it turns out the magnetic field strength inside a solenoid is equal to mu0 times N, where N is the number of turns per length. And actually, this is I. So yeah, you'd expect the magnetic field strength to be higher with higher current. This is number of loops per length of the solenoid. So they might give you this separately, calculate that, or they may just say the number of loops per meter is such. And for the most part, if it's a idealized solenoid where the radius is small relative to the length, the magnetic field strength inside the solenoid is pretty constant. And you can, in an ideal situation, you can use Ampere's law to show that this magnetic field strength within the solenoid is constant. So you kind of, with a wire, your magnetic field strength varies away from the wire, and it gets less as you go further away. For a loop, it's just calculating the magnetic field strength at the center of the loop, one particular position. And for a solenoid, we're saying the magnetic field strength is constant within the whole loop. Okay. So what are we going to do now? Yeah. So we had the stuff in chapters, the optical stuff. But we just did that, and we also did the sound stuff and that kind of thing. So what we're going to do is we're going to cover some of the new material, and then we're going to go back and do one more thing. So we're kind of skipping over the new stuff, going back and doing the old stuff. So this is the heat transfer. So the two things that I want you to be able to deal with, well, there's three things really. One is calculate heat transfer, or we're talking about energy in joules, to change the temperature of a material, including phase change. So we did that in class. And so what it basically comes down to is, if you remember the problem we did in class, we had ice, then we had melting, and then we had water, and then we had boiling, and then we had steam. And we did something like, minus 20 degrees C to 0 degrees, melting occurred at 0. You go from 0 to 100. If you're heating it up from freezing, boiling goes at 100 degrees C. Steam is 100 degrees C up to whatever value. And for the cases where you have a single phase, the amount of energy added in joules is equal to the mass times the specific heat associated with ice times the delta T. In this case, delta T would be plus 20 degrees C. For the phase change, you have the mass of the material times the latent heat of fusion. For water, it's a constant phase, so you go back to this relationship. For boiling, you have the latent heat of vaporization, and for steam, you have a constant phase. So this is for ice, this is for water, this is for steam. Now I could start at any point. If I started at 30 degrees C, then I would go from 30 to 100 and then boil it and then go up to something. So I may not go all through all 5 of these different cases, but I may start in the middle just so it's not quite as long. So review that problem. The second thing was the calorimeter. And remember what we had there is you had some insulated container with usually liquid water in there. I'll definitely use water. And then you take some hot object like this. It doesn't have to be hot, but it could be cold. Most of the time it's hot. So this is going to be, we'll call that T solid initial. And then you're going to have T water initial. And what happens is when you put the rock into the cold water, it cools down and the water heats up and they reach some equilibrium temperature. Just called T final because it's the same. So the energy lost by the hot thing is the energy gained by the water, which is the cold thing. So and this is a solid and this is a liquid, so they stay the same phase. So we're going to use one of these relationships. So what we'd find out is the mass of the solid times the specific heat of the solid times the final temperature, which is the same for both materials, minus the solid's initial temperature, and then you add that to the mass of the water. I guess we'll use W. So the mass of the water times the specific heat of the water times T final of the water minus T of the water initially has to equal 0. So this quantity is going to be a negative quantity, and this one is going to be a positive quantity, because here the temperature goes down, here the temperature goes up, and they have to be equal to each other. So from that, I can ask you, I have to give you pretty much everything except one thing, and then you have to solve for it. Typically, the the temperature of the solid changes much more than the temperature of the water, because the water has a high specific heat, and so to absorb the energy from the hot thing, it doesn't have to increase the temperature quite as much. So that's the calorimeter. And then the last thing is want to calculate the heat transfer through a wall. So that was heat transfer rate. So that's dq dt. This has units of joules per second. Time is seconds. And that's called a watt. Same unit that we used for work or for power. So the relationship is equal to K. Did we use K? I can't remember. K seems like not the one that we want to use, but what page is that? It's page chapter 11, I think. Oh, yep, they did use K. Okay, so it's K times the area, cross-sectional area, times the temperature difference between the high and the low temperature parts of the thing divided by the length. But what we do is we define R as L over K. So this is the thickness in meters. And this is what we call the thermal conductivity. And it has units, well, let's see if we, has units of watts, and this has units of meters, and we divide by degrees C, and we divide by meters squared. A watt is a joule per second. So we're going to have, and this is going to cancel out with one of those, so we're going to end up with joules, meters, seconds, degrees C. Okay, so that's units of R. So if I gave you R and L, you can calculate K. So K is going to be equal to L over R. A lot of times we're given R for the material, for a particular size material, type of material. But if we wanted to figure out what the thermal conductivity was, we could back it out if we knew the thickness of the particular element material. Now, one advantage of using R here, so instead of having the equation like this, you have the area times TH minus TL divided by R. So for L over K, I put in R. The nice thing is that the equivalent, and it's not surprising this is an R, it looks like resistance because it's the resistance to heat transfer, is just the sum of the R's for the individual parts of a composite structure. So I want you to be able to do that. We think we worked out an example in class, but let me just show you how this would be set up. And I can call them whatever I want to, but I'll give them things. So let's say this is drywall, and this is insulation, fiberglass. And let's say this is siding. So let's say the R for the drywall is 1.2 joules per meter per second degree C. Let's say the R for the fiberglass insulation is 8 joules per meter second degree C. joules per meter second degrees C. And let's say the siding is equal to 1.6 joules per meter second degrees C. So if I wanted to find the total R value for that composite structure, I just add them together. Sweet. So that's going to be 8, 9.6, 10.6, 10.8. So it's going to be 10.8 joules per meter second degrees C. So if I asked you to calculate the heat transfer rate, it would be the area. And so let's say the area is 20 cubic square meters. And let's say the low temperature here is 40 degrees C, and the inside temperature, not 40, that'd be hot. That's Fahrenheit. Let's say 5 degrees C, and the hot temperature would be 25 degrees C. So to calculate the heat transfer rate, we just take the area, 20 meters squared, times TH, which is 25 degrees C, minus 5 degrees C, that's the low temperature, divided by the sum of all the individual R's. And from that, we would get a number. Try to find my calculator. Thought I was tethered, but I'm not tethered, so I can roll over here, find my calculator. So you have 20 meters squared times 25 minus 5, which is 20, divided by 10.8, and that would give you 37.0 joules per second, or 37.0 watts. Now, if I asked you to find the total amount, how much energy, which is going to be in joules, is lost in 8 hours, what you have to remember is that the heat transfer is equal to the heat transfer rate times the time. So I've calculated the heat transfer rate in joules per second. And notice joules per second, so that's not seconds, that's hours. So you got to take 8 hours times 60 minutes per hour times 60 seconds per minute. So it's 37 times 8 times 60 times 60. So the total amount of energy is 1.07 times 10 to the 6th joules, or 1.07 megajoules. Okay, so those are the three major problems for heat transfer. First is calculating the total energy in joules, and they're usually pretty big, hundreds, thousands, millions of joules. Calorimeter problem, and heat transfer through a wall. Okay, the last thing that I want you to remember how to do, and we did this on a test, but it was a take-home problem, and that was the whole idea of AC circuits and impedance. So this was how do you deal with an AC circuit where you're given some time varying current, say, and if you remember what we did is we had some amplitude times the sine of some frequency, 2 pi f times t amps. So the current from that you can get, from this relationship you can get that the maximum current is going to be 0.50 amps, because the sine oscillates between 0, -1, and +1. So the amplitude is going to be 0.5. So what we typically have is a circuit. It's an RLC circuit that has a resistor, capacitor, and an inductor, and then you have some kind of time-varying current, in this case current source. So there's a resistance, there's a capacitance, there's an inductance. And what we do is we come up with these reactance values for the 3 different components. So remember, we'll use X to represent the different parts. So the resistive reactance is just the resistance in ohms. For the inductor, it's going to be equal to 2 pi f times L, and that also has units of ohms. And then you have the capacitor, which is 1 over 2 pi f times C, and that also has units of ohms. Now the resistance is in ohms, the inductance is in henries, and the capacitance is in farads. Okay, so this is Henry. This is farads. And the reason it's 2 pi f is because I have 2 pi f in here, where f is the frequency in hertz. So it's pretty straightforward. I'm going to give you a frequency, resistance, capacitor, resistance, inductance, capacitance. You calculate these 3 things. Then you calculate the total impedance for the circuit, which is the square root of x sub r squared plus x sub L minus x sub C squared. So that's because, if we draw this as a phasor diagram, that the resistance goes this way. This is x sub r, and the inductance goes this way, I think. Let me double check on these again. This is chapter 21, and it's all about phasor diagrams. Yeah, so x sub L goes up, x sub C goes down. It's because they're out of phase with each other. And what you do is you add these 2 together, and then the resultant of those 2 vertical vectors is a vertical vector. It could go up or it could go down. Anyway, that's the impedance. And then what you do from that is you can relate the maximum voltage is going to be equal to the maximum current times the impedance. So once you have the impedance and you have the maximum current, because it's given in the problem, you can calculate the maximum voltage, and then you can then do the RMS voltage, which is the maximum voltage divided by the square root of 2, and the RMS current is equal to the maximum current divided by the square root of 2. And what these are the values you use to calculate power dissipated in an AC circuit for the equivalent DC value that you would need to have the same power dissipated. Oh, one last thing, you've got the phase angle is equal to the tangent of the phase angle. It's x sub L minus x sub C over x sub R. So this is an angle. You can either do it in degrees or radians. Okay, so that's all I'm going to put on there. Oh, that's not true. I forgot to tell you. I got one more here. Sound. I do have a sound one on here. And let's see, what did they have to do with? So you've got the string and you've got the tubes. And the key thing to remember here was that, for a string between two supports, you're going to have the fundamental frequency is going to be the strings not moving at the ends, but moving in the middle, going up and down. And we said that creates a half of a wave. So the wavelength, this is L. This is the distance between the ends. So L is equal to lambda divided by 2, or lambda is equal to 2L. So if this is the length, then it takes 2L to make a full wavelength. So that was one relationship. We also had that the wave speed is equal to the wavelength times the frequency, which all applies for all waves. And then we had that the wave speed was equal to the square root of F over mu, where this is your tension in newtons, and this is your mass per length, and that's kilograms per meter. Okay, so it'll be similar to the problem on the previous test. We're just going to worry about both ends here, because it looks very similar to what you have with the string. You have a tube, and because of symmetry, what you have is you have at the center here, you have no movement in the air, but you have the maximum fluctuation in the air pressure. But just like with a string, you have a length of the tube, and for the fundamental frequency, that for this case, when you have your fundamental frequency, you have the same result. The wavelength of the sound wave is 2 times the length of the tube. So if you want to calculate the frequency turns out to be 1 over 2L times the wave speed, which is this is the speed of sound. This is the speed of the wave in the string. The speed of sound is equal to 331 meters per second times the square root of T, absolute temperature, over 273. So make sure you use T as Kelvin. So you can find the fundamental frequency, and in both of these cases, whether it's a tube or a tube and open at both ends or a string restrained at 2 ends, the harmonics are just multiples, integer multiples of the fundamental frequency. So once you get the fundamental frequency, you can find the harmonics. You don't have to go through these equations anymore. So that these both apply. Okay, so I went through that fairly quickly. So don't think, 45 minutes, that's all I need to do to study for this test. Of course, you're going to take time to write it all down. But what you kind of need to do is to understand what the heck I'm talking about. I'm not going to write in a 7-hour video going through every little detail. I'm just giving you the gist of what's going to be on the test, and it's up to you to do the hard work. In real colleges, you might have 4 exams, and you'd spend an entire day or more studying for a single exam, which you should have already known pretty well to start with because you worked hard during the semester. So I don't want anybody to think that all I need is some guy to make a video up and I can summarize everything that I've learned in the whole year or half year in 50 minutes. The purpose here is to give you some highlights to help you out a little bit in writing up cheat sheets, but you're going to have to put in a little more effort. And again, you want to take what I've given you. I'm giving you 4 pages, I think, to do cheat sheets, and not just write a lot of equations and hope you find one that works. The key is that you understand what the variables mean, what the units of the variables are, what the basic concepts are. So the cheat sheet, as much as making it so you don't have to memorize a lot of stuff is to help you organize your thoughts and write them down. Because just reading something and actually writing it on paper, there's a huge difference in the effectiveness. So use these skills, try and teach you some skills for when you go to a 4-year school.